LibreText Introduction to Chemistry 1.2 Chemicals compose ordinary things. Chemistry is the branch of science dealing with structure, composition, properties, and the reactive characteristics of matter. Matter is anything that has mass and occupies space. Thus, chemistry is the study of literally everything around us. The liquids that we drink, the gases we breathe, the composition of everything from the plastic case on your phone to the earth beneath your feet. Moreover, chemistry is the study of the transformation of matter. Crude oil is transformed into more useful petroleum products, such as gasoline and kerosene, by the process of refining. Some of these products are further transformed into plastics. Crude metal ores are transformed into metals that can be fashioned into everything from foil to automobiles. Potential drugs are identified from natural sources, isolated, and then prepared in the laboratory. Their structures are systematically modified to produce the pharmaceuticals that have led to vast advances in modern medicine. Chemistry is at the center of all of these processes. Chemists are the people that study the nature of matter and learn to design, predict, and control these chemical transformations. Within the branches of chemistry, you will find several apparent subdivisions. Inorganic chemistry historically focused on minerals and metals found in the earth, while organic chemistry dealt with carbon containing compounds that were first identified in living things. Biochemistry is an outgrowth of the application of organic chemistry to biology and relates to the chemical basis for living things. In the latter chapters of this text, we will explore organic and biochemistry in a bit more detail, and you will notice examples of organic compounds scattered throughout the text. Today, the lines between the various fields have blurred significantly, and a contemporary chemist is expected to have a broad background in all these areas. In this chapter, we will focus In this chapter, we will discuss some of the properties of matter and how chemists measure those properties. We will introduce some of the vocabulary that is used throughout chemistry and the other physical sciences. Let's begin with matter. Matter is defined as any substance that has mass. It is important to distinguish here between weight and mass. Weight is the result of the pull of gravity on an object. On the moon, an object will weigh less than the same object on Earth because the pull of gravity is less on the moon. The mass of an object, however, is an inherent property of that object and does not change, regardless of location, gravitational pull, or anything else. It is a property that is solely dependent on the quantity of matter within the object. Contemporary theories suggest that matter is composed of atoms. Atoms themselves are constructed from neutrons, protons, and electrons, along with an ever increasing array of other subatomic particles. We will focus on the neutron, a particle having no charge, the proton, which carries a positive charge, and the electron, which has a negative charge. Atoms are incredibly small. To give you an idea of the size of an atom, a single copper penny contains approximately 28 with 21 zeros beyond it atoms, or that's 28 sextillion, million, billion, trillion, quadrillion, quintillion, sextillion. Because atoms and subatomic particles are so small, their mass is not readily measured using pounds, ounces, grams, or any other scale that we would use on larger objects. Instead, the mass of atoms and subatomic particles is measured using atomic mass units, abbreviated AMU. The atomic mass unit is based on a scale that relates the mass of different types of atoms to each other, using the most common form of the element carbon as a standard. The AMU scale gives us a convenient means to describe the masses of individual atoms. The AMU scale gives us a convenient means to describe the masses of individual atoms and to do quantitative measurements concerning atoms and their reactions. Within an atom, the neutron and proton have a mass of 1 AMU. The electron has a much smaller mass, about 0.0005 AMU. So 5/10,000ths of an AMU. Figure 1.2.1 on page 1.2.1. Atoms are incredible small. To give you an idea of the size of an atom, a single copper penny contains approximately 28 sextillion atoms. Atomic theory places the neutron and the proton in the center of the atom, in the nucleus. In an atom, the nucleus is very small, very dense, carries a positive charge from the protons, and contains virtually all the mass of the atom. Electrons are placed in diffuse cloud Electrons are placed in a diffuse cloud surrounding the nucleus. The electron cloud carries a negative charge from the charge on the electrons, and in a neutral atom, there are always as many electrons in this cloud as there are protons in the nucleus. The positive charges in the nucleus are balanced by the negative charges of the electrons, making the atom neutral. An atom is characterized by the number of neutrons, protons, and electrons that it possesses. Today, we recognize at least 116 different types of atoms, each type having a different number of protons in its nucleus. These different types of atoms are called elements. The neutral element, hydrogen, the lightest element, will always have one proton in its nucleus and one electron in the cloud surrounding the nucleus. The element helium will always have two protons in its nucleus. It is the number of protons in the nucleus of an atom that defines the identity of an element. Elements can, however, have differing numbers of neutrons in their nucleus. For example, stable helium nuclei exist that contain one or two neutrons, but they all have two protons. These different types of helium atoms have different masses, 3 or 4 AMU, and they are called isotopes. For any given isotope, the sum of the numbers For any given isotope, the sum of the numbers of protons and neutrons in the nucleus is called the mass number. All elements exist as a collection of isotopes, and the mass of an element that we use in chemistry, the atomic mass, is the average of the masses of these isotopes. For helium, there is approximately one isotope of helium 3 for every 1 million isotopes of helium 4. Hence, the average atomic mass is very close to 4.002602. Now, when it says there is approximately, for helium means for all of the helium in the universe. There is approximately one isotope of helium 3 for every 1 million isotopes of helium 4. So a ratio of 1 to 1 million. As different elements were discovered and named, abbreviations of their names were developed to allow for a convenient chemical shorthand. The abbreviation for an element is called its chemical symbol. A chemical symbol consists of one or two letters, and the relationship between the symbol and the name of the element is generally apparent. Thus, helium has the chemical symbol capital H, lowercase e. Nitrogen is uppercase N, and lithium is capital L, lowercase I. Sometimes the symbol is less apparent but is decipherable. Magnesium is capital M, lowercase g. Strontium is capital S, lowercase r. And manganese is capital M, lowercase n. Symbols for elements that have been known since ancient times, however, are often based on Latin or Greek names and appear somewhat obscure from their modern English names. For example, copper is capital C, lowercase u, from cuprum. Silver is capital A, lowercase g, from argentum. Gold is capital A, lowercase u, for aurum. And iron is capital F, lowercase e, from ferrum. Throughout your study of chemistry, you will routinely use chemical symbols, and it is important that you begin the process of learning the names and chemical symbols for the common elements. By the time you complete general chemistry, you will find that you are adept at naming and identifying virtually all of the 116 known elements. Table 1.2.1 on page 1.2.2 names the names and chemicals. Table 1.2.1 contains a starter list of common elements that you should begin learning now. Table 1.2.1 names and chemical symbols for common elements. If you are drawing this table, it is 4 across and 15 down. So the first 4 are the permanent. Well, actually, it is 4 across and 15 down, but it repeats element, chemical symbol, element, chemical symbol. So 4 across, element, chemical symbol, element, chemical symbol, and then there are 2 rows of 15. They do not include the number, but the symbol only. Hydrogen, capital H, and I'm going down. Helium, so element hydrogen, chemical symbol H. Element helium, chemical symbol He. Element lithium, chemical symbol Li. Element beryllium, chemical symbol Be. Element boron, chemical symbol B. Element carbon, chemical symbol C. Element nitrogen, chemical symbol N. Element oxygen, chemical symbol O. Element fluorine, chemical symbol F. Element neon, chemical symbol Ne. Element sodium, chemical symbol Na. Element magnesium, chemical symbol Mg. Element aluminum or aluminium, chemical symbol Al. Element silicon, chemical symbol Si. If there are 2 letters, the first one is capital, the second one is lowercase. Now, the second set of elements and chemicals, the second 15, element phosphorus, chemical symbol P. Element sulfur, chemical symbol S. Element chlorine, chemical symbol Cl. Element argon, chemical symbol Ar. Element potassium, chemical symbol K. Element calcium, chemical symbol Ca. Element iron, chemical symbol Fe. Element copper, chemical symbol Cu. Element zinc, chemical symbol Zn. Element bromine, chemical symbol Br. Element silver, chemical symbol Ag. Element iodine, chemical symbol I. Element gold, chemical symbol Au. Element lead, chemical symbol Pb. The chemical symbol for an element is often combined with information regarding the number of protons and neutrons in a particular isotope of that atom to give the atomic symbol. To write an atomic symbol, begin with the chemical symbol. Then write the atomic number for the element, the number of protons in the nucleus, as a subscript preceding the chemical symbol. Directly above this, as a subscript, write the mass number for the isotope, that is, the total number of protons and neutrons in the nucleus. Thus, for helium, the atomic number is 2, and there are 2 neutrons in the nucleus for the most common isotope, making the atomic symbol 4/2, but not as in division. There's a number 4, a small number 4, and a small number 2, He, period. Or a small number 4, a small number 2, He. In the definition of the atomic mass unit, the most common isotope of carbon Small number 12 above small number 6, capital C, is defined as having a mass of exactly 12 AMU, and the atomic masses of the remaining elements are based on their masses relative to this isotope. Chlorine, chemical symbol Cl, consists of two major isotopes, one with 18 neutrons, the most common, comprising 75.77% of natural chlorine atoms, and one with 20 neutrons, the remaining 24.23%. The atomic number of chlorine is 17. It has 17 protons in its nucleus. Therefore, the chemical symbols for the two isotopes are 35 above 17 Cl and 37 above 17 Cl. When data is available regarding the natural abundance of various isotopes of an element, it is simple to calculate the average atomic mass. In the example above, 35 above 17 Cl was the most common isotope with an abundance of 75.77%, and 37 above 17 Cl had an abundance of the remaining 24.23%. To calculate the average mass, first convert the percentages into fractions. That is, simply divide them by 100. Now, chlorine 35 represents a fraction of natural chlorine of 0.7577 and has a mass of 35, the mass number. Multiplying these, we get 0.7577 times 35 equals 26.51. To this, we need to add the fraction representing chlorine 37, or 0.2423 times 37 equals 8.965. Adding 26.51 plus 8.965 equals 35.48, which is the weighted average atomic mass for chlorine. Whenever we do mass calculations involving elements or compounds, combinations of elements, we always need to use average atomic masses. Whenever we do mass calculations involving elements or compounds, combinations of elements, we always need to use average atomic masses. For this section 1.2, Contributions and Attributions, this page was constructed from content via the following contributors and edited topically or extensively by the LibreText development team to meet platform style, presentation, and quality. Paul R. Young, Professor of Chemistry, University of Illinois at Chicago, Wiki Ask the Nerd, PRY at askthenerd.com dash PYOUNG at UIC.edu, chemistryonline.com, and Marissa Alviar Agnew, Sacramento City College, and Henry Agnew, UC, or the University of California, Davis. End of section 1.2.